What is quantum wave-particle duality beyond classical analogies? Imagine trying to describe something that acts like both a tiny ball and a ripple in water at the same time. That's what quantum wave-particle duality is all about. It's a strange idea that some of the smallest things in nature, like electrons and photons, don't fit into just one category. They are neither only particles nor only waves. Instead, they have properties of both, depending on how you look at them. In classical physics, we think of particles as tiny points with a specific location and waves as spread-out oscillations. But in quantum mechanics, things are different. Quantum objects are described by something called a wave function. This wave function is a mathematical tool that tells us the chances of finding a particle in different places or states. It behaves like a wave because it can create interference patterns and diffract, just like ripples in a pond. When we measure a quantum object, it suddenly appears as a particle at a specific spot. This is called a detection event. For example, in the famous double-slit experiment, electrons are fired one at a time through two tiny slits. Over time, they create an interference pattern on a screen, showing wave-like behavior. Yet, each electron hits the screen as a single point, a particle. This shows that the wave function contains both wave and particle information, but it does not switch between the two. Instead, it always encodes both aspects at once. This idea is called wave-particle complementarity. It means that wave and particle descriptions are just different ways of understanding the same quantum reality. They are not separate states that the object switches between. Instead, they are two sides of the same coin, depending on how we observe or measure the system. Classical analogies fall short because they rely on everyday experiences. Quantum objects do not behave like tiny balls or ripples alone. Their behavior is governed by the Schrödinger equation, which describes how the wave function changes over time. The wave function itself is not a physical wave in space but a probability amplitude. It tells us the likelihood of finding a particle in a certain place or state, not where it physically is. Understanding wave-particle duality is essential for quantum technology. It explains how quantum bits, or qubits, can exist in multiple states at once. It also underpins quantum interference used in quantum computers and sensors. Technologies like quantum cryptography relying on manipulating these dual properties to secure information. In essence, quantum wave-particle duality shows us that tiny particles are not just particles or waves but a combination of both. Their behavior depends on how we measure them and what we want to know. This duality is at the heart of quantum mechanics and drives the development of new quantum devices and systems.